Good afternoon, everyone. First, I must thank the organizer of the conference to give me a chance to introduce our recent work. This is the title of my talk. My name is Bing He. I come from this institute. Here is the outline of my talk. First is the background, then the works in DT plasmas and Guild plasmas. Based on this, we get our final result. Here is the background. The heating of DT ion by alpha particle is crucial to the controlled fusion. One of the important parameters is the electron-ion energy partition for alpha particle in DT plasmas. Here is the usual definition of the energy partition. In the design of fusion target, some material besides DT are often used. Here gives some structure of fusion target. This picture comes from a paper written by Professor Kawata. You can see that some materials such as gold and aluminum may be used in the target design. During the implosion process, this material would mix with DT fuel inevitably. How the mixed material influence the heating of DT ion is unknown to us. That's the motivation of our work, where the case for DT and Guild mixed plasmas is considered. For this motivation, the stopping power of alpha particle in both DT and Guild plasmas must be first known. Now let's turn to the energy partition in DT plasmas. Here gives three representative works in this field. The first one is for ICF dense plasmas, where the dielectric function of classic two-component plasmas was used. And the second one is for tokamak and binary collision and dielectric function theory were used. The final one is the BPS theory. Its calculation is very complex. Here gives some simple introduction to binary collision theory. And in this theory, a constant Coulomb logarithm was assumed, and the maximum impact parameter in the order of Debye length was adopted. Here is the BPS theory. We think that binary collision theory is not proper in dense and not so hard plasmas, and dielectric response theory couldn't describe the case when the project energy is below the plasma temperature. We notice that the method of to calculation sorting power due to polarization and field fluctuation can solve this problem. And in this model, that the project trajectory differs a little from a straight line. And the projectile may obtain energy from the plasmas when its energy is below the plasma temperature. We generate this to the case for alpha particle in fusion DT plasmas. Here gives the result of sorting power by the present method and binary collision theory. This one is the contribution from the ion component, and this one is the contribution from electron. We can see that although there is some difference between the two models, this result shows that the heating of plasma by projectile will be stopped when the project energy is below the plasma temperature. This figure gives a comparison of sloping power at different density and at different temperatures when the fluctuation is considered or not. We can see that their results are quite different at low projectile energy. By the way, we also used this method for Guild plasmas, but we found it's not suitable in this case. Here gives the energy partition in fusion DT plasmas by different models at different temperatures and electron density. We can see that at low temperature our result is quite different from binary collision theory, and at a high temperature our result is quite from BPS theory. Now let's turn to the stopping power in Guild plasmas. Our method to calculate stopping power can be seen in the two papers. Also our result are our calculation agrees well with the two experiments. In our calculation, that stopping power is obtained in self-consistent way, which basis is the average auto model. In our calculation, the inelastic stopping and the contribution from free electron and nuclear stopping are all considered. Here gives some basic ideas for the average auto model. Here gives our calculation method for inelastic stopping. It's a relativistic plane wave Born approximation. Here gives a comparison of our result with much better method TDSE for the excitation cross-section in this collision system. We can see that at least for this energy, for this project energy range, our method is valid. Since nuclear stopping have important influence upon our final result, here is necessary to give some introduction about it. Nuclear stopping is caused by elastic collision between projectile and the target ion, which is important at the end of the slowing down of projectile. We find that the two old models doesn't work in this case. So here we want to investigate this problem with a more reliable potential and analyze why the old models doesn't work in this case while they are suitable in DT plasmas. Here is the model suggested by Arista, and we can see that some approximations were used to get the final result. Here is the Guild ion potential at different temperature from the average auto model at different temperature. We can see that with temperature rising, the potential becomes much stronger. In our calculation, we use this method of classical binary collision theory with impact parameter considered, and our previous Gild potential is used in the calculation. Here gives our result for the nuclear stopping at different temperature and solid density. We can say that all the curves turn positive from negative when the project energy is around temperature. And all the results are strongly dependent upon the temperature. Here gives our result compared with different models. We can say that there are obvious difference between among these models. Part of the reason comes from the different potential used, and we find that the Coulomb logarithm couldn't be dealt as a constant when the target ion is much heavier than the projectile, where the thermal velocity of the target ion is much smaller than the projectile velocity. And now let's turn to the final result of energy partition in the mixed plasmas. This figure gives a comparison of stopping power in DT plasmas, and the blue line and the red line, and the black line is the result for nuclear stopping in Gild plasmas at these conditions. We can say that in fact in this condition that the Gild is fully ionized. We can say that nuclear stopping in Gild plasmas is much higher than the DT component of stopping power. The reason is that the highly charged state of Gild ion, this one and this one, are important near the end of slowing down of alpha particle. This table gives our final result for different ratio S of the number of Gild ion with DT ions. Okay, here is S, and it's 100 times of the ratio, and all these are the energy partition which is enlarged by 100 times. We can say if S is smaller than 1, the partition usually decreases within 10%, and if it's more than 5, the partition will strongly decrease. In addition, that for the much smaller density of Gild, similar results are almost found. This is a summary of my talk. Thank you all for your attention.
Thank you. One of the experts of stopping power is sitting right there, and I assume also you start with a question.
Okay, so no, it's a very nice piece of work indeed that Professor Bill has achieved. I think that the situation he has really investigated every aspect. He investigated every aspect of alpha stopping in fusion-related plasma. That's really a great achievement. But I think we can resume that in a very simple way by simply adding the ion contribution to electron stopping. And then you see that the conjecture by Brown and so on is not so much validated, because when the ion velocity is smaller than the electron temperature, you can be in a wide regime where your velocity is higher than ion velocity in your target, okay? In that case, you are in a similar situation, you have another better formula. But you did it much better because you include the fluctuation and all that. So I think it's a very interesting piece of work.
Okay, thank you for your suggestion.
Yongtel.
In the calculation, the temperature, so electric temperature, I think a very important influence on this on the energy loss. But the temperature always means the random motion of electrons. If such electron has moving a direction, for example, toward the end beam, is it possible to make some calculation?
You mean that the direction of the
electron,
the
not
electron movement.
Yeah, movement.
And in my calculation, we only consider that the random direction.
Yeah.
And I think that my calculation doesn't include the case that you suggested.
Thank you. It's very nice talk. Can you change to the slide where you have shown that the alpha particle can gain energy from plasma if the velocity is smaller than thermal velocity? Yeah?
Velocity.
Yeah.
Yeah.
Example here. Example. So the negative value, it means that the alpha particle gains energy. Yeah? And is it energy of directed motion or energy of chaotic thermal motion? When alpha particle gain energy, this additional energy will be directed energy of directed motion or thermal chaotic motion of alpha particle.
So the alpha particle will gain energy due to, but in what direction?
In what you
In this direction?
yes, you are right. We think that when the energy of alpha particle is below the temperature, and that it will obtain energy from the projectile, and then at this time that the DT ion will not be heated by the alpha particle. That's what we killed.
Thank you.
You discussed this in coffee. We have a long coffee break. Other questions? I have one. You showed that under these conditions with gold, the potential is very different. It's steep rising. But on the other hand, you put in Maxwell distribution, which is my question is it still reasonable to assume Maxwell distribution, which
I think that for example, for this dense plasmas, I think that the velocity distribution of electrons is different from Maxwellian one. But here in my calculation, I didn't consider that factor.
because it's more easy to
Yeah. Okay.
Thank you. Is there any other question? I don't see that this is the case, so thank you again. And